I'll type that here.
Oops. All right. I think without further ado, we're going to get started. All right. My name is Marcus. I am a member of the Osiris Lab. I'm a senior computer engineering student, and my focus is around hardware embedded in IoT devices. So today's talk is going to be a very high level, like no knowledge inferred talk on hardware and IoT hacking. So we're going to talk about a couple different things today. We're going to do a full intro to hardware embedded in IoT devices, what they are, how they work. We're going to talk about different parts of IoT devices from a technical perspective. We're going to talk about finding the attack surface on IoT devices, which is sometimes harder than it looks. And then I'm going to talk you through some tools, some basic things that you can pick up for pretty cheap that'll get you started and get you going. And then now what? So what you can use this newfound nefarious knowledge for. This talk is very much a first time thing. I don't think that the lab has done a hardware talk in a while. So if there's any knowledge that I've inferred that I'm not getting right, that you know, what's that? Definitely stop me and I'll answer it as we go. That the same goes for anybody joining remotely. Just send a message and Richard will relay your question. Without further ado, let's get started. So, introduction. Primarily, IoT and embedded devices are computers. They're anything that, a layman wouldn't consider a computer that is actually a computer is an IoT or embedded device. The Amazon Alexa, that's a computer. The Nest thermostat, definitely a computer. This toaster is a computer. This toilet is a computer with firmware updates. There's a great Twitter account that you should all be following. It's called Internet of Shit. And it's wonderful. And while this isn't a hardware or IoT device, I think that covering something like the content of this tweet is important because a lot of times when it's not a conventional web or desktop app, a lot of these sorts of things tend to fall into the lap of hardware and IoT hackers, just because we're the ones who tend to do it. So, fun story about this attack and why it's important that, regardless of what platform you build, you're thinking about security. The reason why this happens is because Pokemon Sword and Shield uses local network traffic to attempt to discover other players on your network that also have the game. The port number that they chose at random also just so happened to be Roku's peer-to-peer update port. Roku designed their products because a common use case of Roku's is to have a bunch of them in like an office or hospital or whatever. They're designed that only devices on the edge of your network need to be able to download updates. So if you have 20 Rokus, only one actually needs to download the update from the internet. The others can just propagate over your local network. Unfortunately, the port that Roku chose to do this peer-to-peer update over was the same port that Pokemon chose. And Roku didn't do any validation on the packets that were getting sent over. So when you would start up a Roku on the same network as Switch playing Sword and Shield, it attempted to use the player discovery packets as a new firmware. Because it wasn't signing firmware, it wasn't checking firmware, it wasn't unpacking firmware, it wasn't doing anything. It was just trying to boot. Fun story, fun tangent, and probably pretty different from everything else that we'll be talking about tonight, but I felt like it was important to share. Yeah?
This is all interesting, but more importantly, do you know if Pokemon verifies the packets that get sent to it?
I don't. Nintendo's networking code is usually pretty garbage, so there's a good chance that it doesn't. But there were no instances of a Roku update. As far as I know, there were no instances of a Roku update messing with Pokemon at all. I would assume that they're just dropping the packets like normal fucking people would do. So, back to the basics. If it's smart, it's a computer with extra buttons and extra sensors. And then getting into some other things. Most general IoT that you'll buy off the shelf runs some flavor of Linux if it's not a bare metal firmware, which we'll talk about later. And everything has a web server in it because apparently people can't think of other ways to configure things, which, to be fair, a web server is usually a pretty great way of doing configuration, but it leads to a lot of attack surface. So now we're going to talk about different parts of an IoT device and how those tend to work and what we can learn from each of them. The first thing that we need to understand is what actually does the processing on an IoT device and how that works. So these are all examples of different microcontroller units that are made by AVR, ARM, the 8051 is, I think, Motorola, and these are all processors. This RISC-V one is funny because you can't actually get any of these. There's one board that it currently works on, but it's really, really expensive, so nobody uses it. I've actually never seen RISC-V in an actual device. MIPS is super popular. If you've taken CompArc here, you've probably learned MIPS, or some MIPS adjacent thing. It's nice for some things, crappy for most things, and ARM is honestly the king of everything in the embedded device space, just because it's so cheap. There are so many variants of it, including ones that do low power. Everything in an embedded device tends to be built around power and cost, which makes ARM sort of an obvious thing to do. So now we got to talk about a little bit about what an MCU actually does. It's a brain. You know, this is the CS 101 sort of intro to computer engineering. It's a brain, but we'll talk about it a little bit more. So an MCU is your overall microprocessor. It also has all of your arithmetic and floating point logic units. So most of these processors do floating point right on die. You have a lot of peripherals. This is actually an interview question that I've seen a couple times about doing embedded design is what do you find in an MCU? So counters, which are used for a bunch of different things, input counting. You know, some processors implement instruction counters that way. An ADC is an analog to digital converter. So if you are building an IoT device that's supposed to determine whether or not your plants are watered enough, right? You would have a sensor that gives you an analog output that tells you how damp your soil is. You need some way of reading that. So a lot of microcontrollers have analog to digital converters built in that can translate, 5-volt signal to 1024 bits to a 1024 binary value, and there you go, that's your value. There's also yes?
So each sensor, would that be different for each different type of sensor that I use?
Yeah. So sensors are a case-by-case basis. For analog sensors specifically, it all depends on what the datasheet says and how it actually interprets things. The simplest analog sensor device is called a potentiometer, which is basically just a variable resistor. And the way that you would read one of those is you tie one end to the 5-volt pin, you put the other, to your voltage high, the other one to your ground, and then you measure you use your analog to digital converter to measure the voltage on the wiper pin, which is actually going around a coil inside. And by measuring the potential difference between your high voltage and your middle voltage, you can figure out where the potentiometer is.
But for example, there's this room and the sensor is monitoring if there is any movement or not. On the basis of that, it'll shut off the light. Now,
so you wouldn't do that with an analog sensor. Analog sensors have very, very specific use cases when you are trying to measure something that's continuous. So for a classic example is like a knob. Do we have a marker in here that I can draw with?
Marker is loading.
There's an eraser, but no marker.
Well, how dirty is the eraser?
Give it a sec.
Yeah, right, just grabbing it.
So we're gonna give that a second.
got reads on it.
So the sensing that you would do for a, it's funny that you would like mention like a room motion sensor, because those generally tend to be their own enclosed devices. So you can buy a fully packaged solution from a vendor that does motion sensing, and then just communicates over a serial bus, which we'll talk about in the next couple slides.
So I could use the same ARM processor and connect it to the one for the light, like for shutting off the motion sensor, as well as for something that will measure the plant water level as well.
Yeah, absolutely. Absolutely. They'd be on different peripherals on the microcontroller, but there are microcontroller units that can absolutely do both of them. For example, the Teensy 3.2 or 3.6 is a microcontroller like dev board that has an ARM micro on it, and can do analog to digital conversion, bus reading, all of that. Wonderful, thank you. All right, so if Richard wants to turn on his camera so that everybody remote can see this too. So, in the classic example of like, we're going to call this a knob, right? Let's pretend that this is a, can everybody see this? All right, so if we're building like a speaker, right, we have a knob, what that looks like in the schematic, this is VCC. So what this schematic demonstrates, and what it would actually, I'm also going to show you what it, so this is what the schematic would look like, and then if you are talking about how it would actually be connected to something, I'll draw that too. So you connect one side of the device to a high voltage, you connect the other side of the device to ground. Inside there's a coil that's wound really, really tightly that has a resistance to it. I'm glossing over a lot of the actual electrical engineering shit. If anybody's in EE and is actually checking me on this, I know I'm wrong, it's okay. So what you do is you read because there are 3 contacts inside. One contact is at the front of the coil, one contact is at the other side of the coil, and then the last contact is on a wiper that can move around. So it's an arm that's like touching the coil at different spots. Depending on how far down the coil you touch, the higher the resistance you see, so the lower the voltage you see. Does that make sense? So you take this value and you connect it to your analog to digital converter, which is a peripheral on your microcontroller, and it can tell you what the voltage is at the wiper, and then you read the data sheet for the part that you bought, because it's all based on what parts you buy, different values. That can tell you what real world value that signifies. So for example, in this one, if high is 3.3 and ground is 0, and we have a reading of like 2.7, we can figure out by doing 2.7 over 3.3, oh, this must be 30 degrees to the left. Make sense? It all comes down to reading a data sheet, because the only thing that ADC can actually tell you is voltage. On the flip side of that, you have something called a digital to analog converter and something called PWM. PWM is pulse width modulation, which is just a way of getting put it back over here, which is just a way of getting a voltage different from the one that you have. It's shitty, but it can also be used to control a bunch of things. And a digital analog converter is a much cleaner way of getting a precise voltage. So if your entire processor runs at 3.3 volts, but you need 2.2, for example, you can do that with PWM by turning a 3.3 pin on and off really, really fast, and the apparent voltage will be 2.2 volts, but that's crappy and not good enough for doing audio, for example. But an analog to digital converter has a much nicer method of getting a good voltage, a good stable voltage out. Going back to the microcontroller unit itself, It also has the ability to interface to other devices over buses and things like that, which we'll talk about in a few slides. The next thing that we're going to talk about is flash memory. There are no hard drives on IoT devices. Fun fact, Western Digital used to make really small, like quarter-size hard drives, like the size of a US quarter, to go into iPods. They had really ridiculous failure rates, but they were really cool. We don't do that anymore because flash storage is super cheap and really easy to use. IoT devices themselves don't have hard drives, and microcontroller units themselves usually don't have any storage. They'll have cache, like processor cache, but that's not good enough for, they'll have cache and they'll have RAM, but that's not good enough for actually running code. So enter flash memory. They store anywhere from the bootloader that the processor uses to boot itself up, to the application code that actually runs on the device. That includes the things like the web server that you can connect to set it up, and all of that, to long-term data. So for example, if we're doing like a gardening thing, we can store, logs of every time we've watered the grass or whatever, or if it's like a room monitoring thing, we can store like whenever we turn the lights on, whenever we turn the lights off. If we're hacking an IoT device and we can't find the firmware online anywhere, one of the first things that we're going to go to is we're going to pull the flash off the board. So that means different things on different boards, different things on different types of devices, but you are literally removing the physical chip and reading it, because 9 times out of 10 they're not encrypted. Actually, I would wager that 99 times out of 100 they're not encrypted. Lots of different interfacing, I2C and SPI, which we'll talk about on the next set of slides. Different package types. So chips come in what are called packages, which is the actual physical chip you see on the board. Say I wanted a flash chip, right? I could have a flash chip that has 8 legs, kind of looks like a bug. That's a flash chip, right? I could have that same silicon in a form factor that just looks like a square that has the balls underneath, because those are 2 different types of packaging for the same chip. Any questions? Cool. There are lots of tools to dump flash. We'll talk about them later. Buses. They're the IoT devices all have memory, of course, but the analog to what a bus is in importance to an IoT device versus a traditional system is memory. If you can read memory when you're like attacking an application, you win. If you can read a bus and understand what's going on that bus on an IoT device, usually you can win too. At least for the parts that involve sensor reading. There are 4 different types of buses that we're going to talk about: UART, SPI, I2C, and Jtag. They allow for the flow of data and information between different components on an IoT device. Your microcontroller doesn't have an accelerometer built into it, but you can buy an accelerometer off the shelf and then talk to it over SPI. By being able to listen to a bus, you can find out a lot about what information your microcontroller is receiving and what it's outputting. And sometimes developers will even leave shells on there, so we'll talk about that in detail. SPI stands for Serial Peripheral Interface, and it is 4 physical electrical signals per device. So you have a chip select, a master out slave in, master in slave out, and a clock that the master drives. And the way that this works is that you have 2 devices. So let's say that you have a microcontroller and we can use the motion sensor for this one, because this is a good one for the motion sensor. So the microcontroller we're going to call the master, and what the master has is a clock that it continuously pulls. That it continuously sets high and low, so tick, 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 continuously, right? Now, you don't always want to be checking your sensors, because sometimes that's too frequent, your data doesn't matter, and it'll cost you a lot of power. So what you do is you hold your slave select for the particular sensor, because if you have multiple sensors, you need multiple chip select lines. You hold it high until it's time to actually read from it. So you signal the device that you want to read from, and then you send it a message, and it sends you back a message. So going back to the example of the room sensor, right? it's time for me to read whether or not there are people in the room. I have the clock going the entire time, tick, 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 tick. I pull the pin for wherever the sensor is connected, wherever its chip select line is connected. I pull that line low, and I send a message. I'm like, I want to know if there's movement, which is an instruction that the device can understand. So I send it, OX6F or whatever, and then it has another 8 clock cycles that it can send back a response. And then I put the line back high and wait until it's time to do that again. And that's a really...
So the wait time increases as and when, or it's constant for each?
Constant.
Would there be an ABC in between?
No. I'll get to that in a second. So the way that data actually gets sent back and forth is by a digital signal, by a 1 or a 0. So on this diagram, you can see that when the line, every time the clock goes from low to high, we have an arrow. That arrow means that we are taking the value at that time. So when the signal, this is the master out signal. When the master out signal is high and the clock goes high, we call that a 1. And when it's low and the clock goes high, we call that a 0. So by taking advantage of just being able to pull this line low and high in relation to where the clock cycles are, we get binary data. We get purely digital data that the processor can understand without having to do any other conversion. Because it just stores it in a buffer internally, puts it all together, and then boom, that's the value. That's the beauty of using a serial port, because all the data is already digital.
But it's actually a sine wave, which is just
No,
modulated.
this is not a sine wave.
Okay.
This is a square wave that is very clearly defined to have highs and lows.
Okay.
Granted, the signaling on the bus might have slight curves to it, but that's just because of like parasitic capacitance. Internally, it doesn't care. It's just literally checking if it's high or low. High is like a specific threshold. Low is anything below that threshold. There's no analog magic going there at all. Any questions?
So like there isn't any encoding also coming into factor?
The encoding is like application specific.
Like you said that if I could tap into the data of the bus, I could get a lot of data. I could read it. But shouldn't there be some encoding present before the data goes through the bus so that even if somebody taps in through the bus, they don't?
See, you'd think, but no. Specifically for sensing, there's almost never. You can do, so flash chips, interestingly, a lot of them speak SPI, and this is how you interface with them. If they don't explicitly have like a secure mode or an encrypted mode, you are literally just shitting bytes back and forth over that with no protection. That's why buses are so vitally important to hardware hacking, because granted, good devices don't use these, like expensive devices like computers or mainframes that have embedded components to them don't necessarily use things like this, and are generally better about encrypting and protecting them. But for like the IoT device that you're going to buy for $20 off Amazon, they don't care.
What would be the benefit of encrypting the traffic between two devices within the same box?
Almost nothing.
Okay.
The other thing is that it fails a cost-benefit analysis almost every single time.
Yeah.
And that's what you also, when you're hacking these devices, you're not only hacking the device, you're also hacking the like business unit that made the device decision. Because that's not a joke. In software, it's really easy for like hacking software to be like purely just hacking the software, because yes, there are sometimes business costs to doing things like encryption, but they are measured in developer hours. With these devices, usually security features are measured in actual like dollars and cents on components per board, in addition to programmer hours. So that's why, with sensing it also really doesn't matter, because you already have that sensor, like it's in your house, you know what it's sensing. So to encode that doesn't really necessarily make sense. Additionally, you have to know you have to know what both components are to be able to actually understand, right? So this is, there's a protocol, there's like an application layer protocol on top of this electrical protocol for all of these devices. And that protocol is only really understood if you have the data sheet for the device in question. Because that motion sensor that you have might have, a really weird way that you need to pull it to actually get the information about whether or not there's movement, and its response might be really strange too. You need the data sheet to be able to understand it. Granted, that's security by obscurity, but it's not nothing. It's not like, you're getting an ASCII message back saying that somebody moved.
Do different sensors require use of different buses?
Yes. So another bus, so SPI is nice because it's really, really simple compared to other things. There's an explicit clock, so you don't have to worry about real timing problems. There's chip select, so you don't have to worry about addressing. And then this is like the simplest serial you can possibly get, which is actually one of the reasons why I showed it first. Then you have I2C, which is the opposite of all of that, and is a really painful, is my microphone muted?
No, I think people can hear you just fine.
Is a really painful protocol to use, at least in my opinion, because you only have 2 lines, but you can have as many devices as you want. What that means is that the protocol that you actually send has to be more complex. Just like in SPI, you have a clock line, but the clock line is only controlled by the master initially. And the first thing that you send is an address for the device that you want to talk to, followed by any actual data that you want to send back. And that, yes?
Question for both I2C and SPI.
Mm-hmm.
Is there a need for like the master and slave to exchange some kind of initial information to synchronize the clock?
No.
No.
In SPI, the master is the only device that runs the clock. In I2C, the clock is handed over. So it's understood that after whatever this is, 8 or so clock pulses, that it is now the responsibility of the slave to drive the clock for 1 cycle, and then it's the master's again, and then it's the slave's again, and then it's the master's again. So that's inherent to the protocol who handles the clock. SPI again is really, really simple for that because the master's always got the clock. I would argue that on some devices you could even do a clock just in hardware with an oscillator, because it's so just, it's always driven by the master. So I2C we're not going to get too deep into, but all it's got is data and clock. You can have up to 256 devices on the same 2 wires, which is really, really nice for layouts where you're being told that you need to really constrain PCB traces. You don't need to do a lot of routing for it. You don't need to tie up a new pin for each device like you do with SPI. SPI, every single device needs its own chip select, and that gets difficult quick if you have a lot of devices. With I2C, it doesn't matter, they just all have to have an address. So that makes I2C more of a network-like protocol, which is more familiar to the people in this room, I would say, than SPI, which is purely just hardware. If you can see it, you can listen to it. Yeah, it's really, really complicated and bad. Clock stretching is a thing, and it's basically just a way of one device telling another device, wait, I'm not done. And it's really complicated, awful protocol, but I'm teaching about it because it's important because it gets used a lot. And it gets used a lot because it's cheap to implement. Jtag.
Quick question?
Yes.
Is there a reason not to implement the same kind of protocols that are done with wireless, like, I don't know, slide LoHa or carrier sense multiple access with collision detections or something like that?
Too complicated and expensive.
Okay.
You don't need it. I2C, these protocols, these wire level protocols are all significantly simpler than anything used for wireless or wired for the most part, because they don't have as much complicated routing demands. So they're kind of like just simple enough to be okay. Good question?
No.
Okay. Jtag I'm going to really, really briefly touch upon just because it's important to hardware hacking, but it's really difficult, and I'm not going to go into depth on it. But it's important that you understand that it exists. It gives you direct processor state access, which is great. It gives you, I think it's like ring -1 access technically, because you can actually view processor internals, which is not something that you get super regularly. There are a lot of different variants. You have something called single wire debug, which is specific to ARM devices. That gives you like full processor inspection, so that's really cool. Jtag is super powerful if you can get it to work properly. And the reason why you've heard of Jtag before is that it was used in hacking the Xbox, and the PlayStation 3, PlayStation 4. It's very popular in the video game hacking community because Jtag is primarily used in development for debugging and for programming. So a lot of manufacturers leave those ports in, and they were used by like the Xbox 360 hackers to be able to like modify consoles and things like that, which is almost literally the only reason why I put this in. And then UART. If it's called Serial, and nobody's been more specific than that, and it's an IoT device, so I'm not talking about like a huge old big iron mainframe, it's probably UART. It's a super, super, super common protocol. It's really simple. It's really easy. And it often comes with a console on the device. So what's not to love? The way that UART works, both devices in their own software. So there's a little bit of a preamble, but I'm not going to get into it because you would only need it if you were implementing UART, which you're not going to. But the devices set for themselves the clock speed and the encoding. So however many bits are in a byte, if you've got like safety checks on or not, and then they just talk. You have one transmit line and one receive line. You can transmit and receive at the same time if you want, but you can only talk to one device at a time. So device A and device B. Device A's transmit is connected to device B's receive and backwards, and then they can just send signals to each other back and forth. And just, it's understood when you start that everything after that is just the predefined clock rate apart. So it's like SPI, but no explicit clock. Each device maintains its own internal clock. Yes, that can lead to a lot of trouble, but most device manufacturers have it working because this technology is older than me, older than all of us, probably. Like, I think it came out like the 70s.
If it's that old, shouldn't it be called DAWART?
Universal asynchronous receive transmit. Thank you.
Oh, okay, sure.
So now that we're done talking about buses, let's get back to IoT devices and their different parts and the ugliness in them. Everything is network connected on IoT. Like all IoT devices are network connected. It's in the name, Internet of Things, which is great because it lets your TV talk to your toilet, but is bad because it lets your TV talk to your toilet and your hacker talk to your toilet and your hacker talk to your TV, and everybody can mine Bitcoin on your shit. So. Network things to look out for on IoT devices. They all have SSH, almost all of them. People are lazy. If it's a Linux-based firmware, it has SSH on, almost guaranteed. Telnet. Telnet's really old. There was a joke about some hacker conference was doing a trivia thing, and nobody in the crowd knew what the port for Telnet was. First of all, it's 23. Second of all, if you do IoT hacking enough, you will remember it because you see it all the fucking time. Almost all these devices have web servers for configuration. Even if they're not running on 80 or 443, they probably have a web server somewhere in them. And on these you see a lot of Python, weirdly. PHP is never going to die, because why would it? Mix of other platforms, I've seen some really weird like ASP shit in the past. It's not nice. Everything on the Intro to Web Hack Night presentation would absolutely apply to all of these devices. It's 2005 on all of them. And what I mean by that is you don't see a lot of modern protections on IoT devices because they're usually written with reused code, sample code pulled from the internet, developed by the lowest bidder, all of that. And phoning home to backend services, I've seen some really, really weird things where devices will like explicitly blacklist certain IP addresses, or every time they turn on will like phone home and send a message to a backend service, even if you don't know about it. It's shady, it's crappy, but it gives you some attack surface if you want to see if they, sanitize their input on that backend service, which they don't because they trust their devices. Firmware is just crunchy software. It's software with extra steps. Ghidra is surprisingly good at firmwares. Most of the time. I've actually just now run into a problem with it, but usually it's fine. So there are three super predominant types of firmware. Real-time I'm going to go bottom to top this time. Real-time operating systems are complicated, and I'm not going to explain them because I don't really know if I can properly do that. It's basically just an operating system that guarantees that everything will happen in a certain period of time, which you need for things like cars, where if you didn't do that, they would hit somebody. Sometimes they do anyway. And then you have Linux-based firmwares, which are super nice. They throw a small Linux image onto a device. Every CTF challenge that you've ever seen probably is actually a binary running on an IoT device somewhere, because all those weird tricks that you can only do in CTFs because modern computers all have ASLR on and all have stack protections on and all have that. No, that all still works on IoT devices because some of them just don't do shit. They're usually specialized distros, which gets a little messy because you don't always have the utilities that you think you have. But the broad strokes are the same. And a lot of them use BusyBox, which is a Swiss Army knife style binary that can pretend to be ls, can pretend to be cat, can pretend to be cd, can pretend to be basically, if you can name a standard Linux binary, BusyBox has a version of it that will do the same thing, which is useful for some things and bad for others because you can't take advantage of, setuid binary bugs. It's just a little bit different. It's different enough to be uncomfortable. And then you have bare metal real-time operating systems. Bare metal firmwares, which are literally a binary that is compiled and targeted at that particular microcontroller that the bootloader just yeets into memory and sets the instruction pointer to, and it goes. Hard to reverse engineer because it's very, very, very architecture specific. Depending on what architecture you're working on, sometimes they do architecture specific tricks. It's hard. It's not always impossible. It's just annoying. You usually see this on really embedded devices, and particularly things that don't do much networking. Because if they did networking, they'd have to write a network stack from scratch, and at that point you'll just use Linux. Now that we've talked a little bit about understanding these IoT devices, let's talk. So you've got a target in front of you. Now what do you do? So one of the first things that I like to look at if I'm doing an IoT thing is physical surface. So you take the device, you take it apart to get at the circuit boards, and then you start looking for test points, which I'll show on the next slide. Unpopulated headers, so places where they obviously meant to put another port but didn't actually solder it onto the board. Random looking USB ports that just don't belong. And dip package chips with accessible legs. Dip package chips are the ones that look like little bugs. You can get chip clamps onto them super easily, and you can read information off of them. These are a couple of examples of everything I just talked about. So all of these gold circles that you can see here, so on the bottom right one, the one that's labeled TP9 for example, that is a test point that they were using during manufacturing and during device development to make sure that when they were sending signals around the board, the signal that they thought they were sending was actually getting sent. These are, and I'll explain why they're useful in a second. This chip, upper left-hand corner, very upper left-hand corner, is, I believe, an SOIP, which is similar to a dip package. And what's nice about this chip, it's kind of bug-shaped. You can get you have little like test clamps that you can clip directly to these metal legs, and you can read signals off of those. So any chip that's having a conversation through one of these legs, you can see what the signals are over them. And then right over here, you can see, and on this one also, this one's probably actually Jtag. You can see that they definitely meant to put a header here. They definitely meant to put some kind of port here, but they didn't. So it was probably used when they were developing it, which means that it's probably still connected to some goodies if you can, connect to it and see what's going on. Any questions on this slide?
So the flatter chips with the big one on the left.
This one?
Yeah. You can't as easily hook onto those legs, can you?
You can. They're just more specialized tooling for it. The nice thing about DIP packages and like SOIP packages and all of those is that the pins are pretty big and they're pretty far apart.
Right.
So you can use cheap stuff that you get off of Amazon for $10 or $5 to clip to them really easily. These you can get like specialized clamps for that actually just like you attach to the entire chip. Granted, you have those for this kind too, but what it does is it'll get all like 40 legs on this side at once. Pain in the ass to actually evaluate because there's only so many signals and logic analyzers you have on hand. But it's nice because you can just get all of that. Nothing is safe if you're sending it electrically around the board. Nothing, like everything can be read somehow. I don't have it on this slide, but we talked earlier about pulling flash chips for getting firmware, right? What that means is that sometimes, so let's pretend that this chip, for example, is a flash chip. I don't know what it actually is, I haven't looked it up. But if this is a flash chip, we can easily put a chip clamp over it, and we have access to all of the lines, and now we can use a flash dumping program to just get the entire contents of that chip off, unless it's using protections, which it's not. This is, I believe, a $30 device. It's not using protections. We can do that with, I don't have any on this slide, but you can also do that in cases where you have QFN or I believe they're like BGA chips, where they have the balls, they have contacts on the physical bottom of the chip. You can actually physically heat the chips up and pull them off of the board to read them. Your device is never going to work again because the odds of you being able to get it back down in the same state are almost zero, but you will get that firmware off that device. So, yes?
If you could go back to the previous one, what do those small holes actually use for?
Which ones?
So like in the Explorer one, just above the E.
This one?
No, so the Explorer is written, and just above the E there is a line of small holes.
Oh, these?
Yeah.
Oh, these are just vias. So this is a PCB, this is a circuit board design thing. There's a signal on the other side of the board that needs to get routed, and this is how you connect the top side to the bottom side. Sometimes vias are useful because they serve as like pseudo test points that you can also connect to. So that's a good point to point out. But usually they don't matter and they're too small to reliably connect to anyway. Alright, that's great. How do we actually hack this? So, I mentioned before a logic analyzer. And what a logic analyzer is an FPGA that is programmed to literally just read its own pins really, really, really fast. So you connect your logic analyzer to whatever test points you found, to if you found like chip legs that you want to clip to, you connect to it, you run the software, and it shows you the waveforms of the signal. So if it's high, low, some of them do analog signals, but usually digital is enough. You have clip probes that I'll demonstrate at the end that just neatly grab onto things. And you connect them to your logic analyzer and then use a program like SIGROC or the SALI logic program to read the waveforms from the device. So it'll show you when, let's say that you clip to a pin on a chip, right? The logic analyzer will show you when that pin goes high and when that pin goes low. these programs also have a bunch of built-in decoders on them that can natively understand UART, can natively understand SPI, can natively understand I2C, Jtag, even USB, some of them, because USB is just an electrical signal. So those built-in decoders can tell you a lot. If you successfully connect to like a UART post, for example, the decoders will, you say, I think I have UART on pins 2 and 3, and the decoder will try its best to like get out the letters for you. And a lot of the time that actually just works. A nice shortcut to doing all of that is to just figure out what different waveforms tend to look like. After some experience, like after a while of looking at these things, I2C is like very distinctly clear versus SPI versus UART versus Jtag. You start recognizing them over time, and that saves you a lot of time in actually doing your hacking. If you see text on UART, it's probably some type of shell. Peripherals don't tend to speak straight serial to each other, and they almost always never speak. They almost never speak ASCII to each other. So if you see words, you probably have some sort of interface directly into a process running on the microcontroller. We also have network surface on all these devices. There's not really too much to say about network surface on these devices. They kind of go the same as a normal network pen test. You connect it to a network that you own and have full control over. You port scan it, so Nmap with all the bells and whistles. You sniff network traffic to see if it's trying to reach out somewhere. Anything that you would do in a regular network pen test on infrastructure or on an application, you would do against an IoT device. But the nice thing is, it's in your house, so you don't have to worry about being careful. You don't have to worry about being quiet. You don't have to worry about, rate limiting yourself so that you don't get rate limited. You don't have to worry about them coming after you with a CFAA violation, because it's not. It's your device. Who cares? So really, go hog wild. It's fun. Web. Connect to the web interface. Do your normal web thing. XSS is very common in a lot of these. You might ask, why does XSS matter? Well, because you can privilege escalate on local devices. Routers, for example, are lousy with XSS. And if you, as a unprivileged user, can inject into a field in XSS that steals the router admin's cookie, you can just go and change your settings. Command injection is super common. CSRF, yeah, sure. Basically, if it's a lot of the introductory web stuff still applies. Like, you don't need to do cool, fun tricks because, the mindset of an IoT developer is that, people aren't going to try to attack these devices, and that's the kind of thing that gives you like really bad errors and really weak devices. So reverse engineering the software running on the devices is its own sort of challenge. A lot of the time, device developers have the firmware available directly on their website. When they do that, that saves you hours and hours and hours of crap. Download it, do what you need to do to extract it. Over time you'll learn how squash file systems work, how flash images work. If you can't get the firmware from the website, then you have to pull the flash. And that gets tricky, but it's not that hard, with practice. I say that it's not that hard. Everything's going to be hard at the beginning, but with practice and with perseverance and just trying things on devices that you don't care about destroying, eventually you can get good at it. But sometimes Flash isn't the easiest option. Sometimes Flash is not doable because they actually went and protected their Flash. At that point, you kind of have to throw away the reverse engineering part of it and do just a black box pen test on the device itself, which is annoying, but not the worst thing. So, now that I've talked a little bit about IoT devices, what they are, how to hack them, I'm going to talk pretty briefly about tools and how to get started. It's an investment because you have physical devices. It's not as simple as just spinning up a virtual machine and hitting it. But just because it's an investment doesn't mean it has to actually cost you a lot of money. The following section, I'm going to describe $30 worth of tooling that can get you started hacking pretty much anything. Well, that and a set of screwdrivers. Raspberry Pi 3B or 0W. The reason why, and this is one of my favorite devices for hardware hacking, it gives you 3.3 volt GPIO. GPIO is general pin in out, so you can control a set of pins that all have 3.3 as their logic high, which is nice because a lot of IoT devices are 3.3 volts. Contrary to like what Arduino would have people believe, most IoT devices operate at 3.3 volts, not 5. So having an easy set of 3.3 volt pins that you can just control means that if you want to mess with devices super easily, it's not hard. There's native serial support, like it has a UART on there that you can just attach things to. PiScope can be used as a crappy little logic analyzer. It's not great, it's not fast, but for slow serial and things like that, it'll give you an idea of what you're seeing. It's got graphical Linux on it, so it's not, there's not this huge barrier for entry for being able to understand it. It's really beginner friendly. There are a lot of resources online. There's built-in Wi-Fi, which is always helpful. I like to use them as like network things too, so they like stand up their own Wi-Fi network, and you connect to it as a user on your laptop, and you connect the IoT device to it, and you can like get really good packet inspection on there. It's really cheap. The 3B Plus is I think 20 bucks, maybe 30. The 0W is 10 bucks. I would personally stay away from the 4 right now because they did some dumb things and you can't use USB and HDMI at the same time. Or maybe it's HDMI and Wi-Fi. I don't know. There's some weird thing that they broke. So yeah, 3B Plus is like the gold standard for me. They're really cheap. You should get one. Even if you don't want to do hardware hacking, you should get one. Cheap logic analyzer. It's 11 bucks. It's literally the one that I've used like the most recently. I have a really nice like $500 one here with me, but the $11 one is absolutely good enough for most of the things that you do. You can read USB off of it because obviously not USB is way too fast, but for any IoT device that you're hacking, an $11 logic analyzer will probably be good enough. It pretends to be the Sali, which is the really, really expensive, really nice one. Like it just tells the computer, hey, I'm a Sali, which means that you can use the logic software that comes with Sali with it, which is good because that's really, really powerful software, really good software. Make sure that you pick up good probe clips that you can also find on Amazon that are really easy to hook and connect. Finally, USB serial adapter, which is also called a USB FTDI, is probably the easier way that you'll find it. This gives you a nice two-way UART. So if you see a UART console on a device, you can connect one of these devices to it, and it shows up in Linux as a TTY device that you can just attach a serial console to, and it just talks back and forth. Really, really simple. They're slow enough that they even work in every VM that I've tried. VMware Player and VirtualBox, I can personally vouch for. They just pass through, like, without a problem, and you can talk to devices. They're cheap and easy. I think this one is like $6 on Amazon. Miscellaneous things that I didn't include in the price. Soldering iron. So sometimes you have test points that you can't clamp. Sometimes you have little chip legs that you want a better look at. Learn to solder to them. Magnifying glass, it's easier to see traces, it's easier to see test points, it's easier to understand what devices you're looking at, it's easier to see chip numbers. A Wi-Fi dongle, or two, because it's always nice to be able to spin up an extra network or pretend to be another Wi-Fi network. Sometimes devices are vulnerable to like evil twin attacks where you can have two APs with the same identity and you can get it to switch between them, which is nice for when you're doing like less IoT devices, but more like industry embedded devices. You'd be surprised at what some really crappy devices don't really care what Wi-Fi they're connected to. Radio stuff that I didn't get a chance to get into in this talk, but Bluetooth, Zigbee, Z-Wave, all of the home IoT radio stuff. They have dev kits for them that you can get online for like 20, 30 bucks a piece. And then there's good open source tooling that lets you like inspect what your thermostat is actually saying to your home automation center. And then SD cards, flash drives, whatever. Some of these devices are really nice, and they'll just boot off of an SD card for you. You don't have to say anything, you don't have to press any buttons. You just stick an SD card in with a firmware image, and it'll boot. How easy is that?
Question.
Yes.
What do you think of GNU Radio?
GNU Radio is a little bit of a different use case than this. GNU Radio attached to what, like a general SDR?
Just to kind of do, understand what is being sent wirelessly from a device.
GNU Radio's major issues come in the fact that I don't really know of good packages that output it to other tools. So for getting an understanding of what actual bits are going over the air, it's fine. It's just going to be a little bit cumbersome to get that into a tool that can actually understand different protocols. Whereas if you buy a dedicated, like Zigbee dongle, for example, there's like the Killer Bee suite that just works with it. So you have all of this knowledge, you have all this understanding, you've spent $30 on Amazon, now what? I'm going to let this slide stand for itself. You know, just buy crap, be consumeristic, break things. There is an entire home automation section on Amazon, sort by price low to high. It's just, it's that easy. I'm just saying. I'm just saying. I'm not responsible if you blow up your house. I'm just saying. Questions?
I have a question. I understand a lot of firmware is written in C.
Yeah.
Does that make it more vulnerable because of, issues with C?
That's why I said that every single CTF challenge still exists as a running IoT binary somewhere. Because you see like really dumb shit like stir copy, buffer overflows. A lot of these devices don't use things like stack canaries because they're using a pared down version of Linux that doesn't necessarily include them, or they've written a bare metal real-time OS. And stack canaries work a little bit differently on ARM as well, so they just don't show up as often.
So you're saying like stack canaries can
Sometimes they're just not there.
because they slow down the program running, therefore in a real-time operating system you don't have it?
Oh no, not necessarily real time. I meant like bare metal operating system.
Oh, okay, sure.
Like when you're writing a bare metal firmware, you're not gonna write a stack canary utility because it doesn't make sense. Unless you actually designed with security in mind, which nobody does.
Someone was curious about, how about a heat gun? Is that a good piece of equipment?
Yes and no. Heat guns are useful for desoldering things and for getting them back on, but they are not the best option for getting chips off. If you're really interested, they're good because you can spend $20 on one and get things that work passively, but unfortunately that also means that you tend to melt the entirety of the board around the heat gun. What I actually personally like is you go on AliExpress, you spend $150 on an infrared table, which is not actually infrared, it's just basically an easy bake oven light bulb and a hot plate, and you heat up the circuit board, and then you put a really, really bright light on that particular chip, and it just comes off.
Oh, wow.
It takes a while, but once you get good at it, it's really fast.
Why not my oven?
Huh?
Why not my oven?
Oh, you absolutely could do it in an oven too, but you just wouldn't want to cook in that oven afterwards. What used to happen is that, if you remember the Xbox 360 Red Ring of Death, that was actually a bug caused by a shaky solder connection on the Xbox 360 hard drive. One of the solutions, well, there were two solutions to the 360 thing. One of them was that you could put it in your oven on 350 for a couple minutes, and it would essentially reflow the motherboard. So that worked, right? The other solution that I personally like a lot better was you would wrap your Xbox in towels to prevent it from cooling, and then you just run it. And it would heat itself up so much that it would reflow the solder inside. It took longer, but you didn't use your mom's oven, so nobody got mad at you. Except the fire department if they showed up, questions, comments, IoT story time? I don't know.
Yeah, so if one were writing firmware and wanted a good programming language to use, what would you suggest?
I mean, firmware is still predominantly written in C, and the reason for that is that tool chains for these devices, like it's not like you're writing for a desktop where you just have GCC and it just works. You need to have tool chains for whatever devices you're using, and most of the tool chains just include a fork of GCC that has support for that particular processor architecture and peripheral set. So you're often just tied to the fact that that's all the tooling that you get. There have been a lot of movements to write firmware in Rust, which is nice because it's memory safe. Go, which is just because people like Go, I guess. I don't understand it. It's got a garbage collector. I don't necessarily think that's great, but people much smarter than I am are doing it, so I'm sure that there's some credence to it. A lot of devices used to be, and even sometimes still are, written in like a JVM language because they just have JVMs that the chip understands. SIM cards, for example, are Java cards that just have a hardware implementation of the Java virtual machine on them. So your like phone runs Java even if it doesn't actually run Java. Yeah, I think this was just about the amount of time that I told people this would take.
Yeah.
If you're interested in hardware hacking, or you want to talk more about it, I'm always in the lab. I've got, if anybody wants to see like what an actual circuit board, test point finding sort of mission looks like, I have a sample up here with me. But other than that, thanks for listening.